Hello everyone. My name is Junichi. Welcome to session 6, titles, Multilingual, and the evaluations. So in these sessions, we have 5 papers on those topics. And yeah, as usual, we have 24 minutes for each. And first one, the first paper is titles, factors affecting the evaluations of synthetic speech in context, and then presentation will be given by Johanna from Edinburgh. Please unmute your microphone and go ahead.
Hello everyone, my name is Johanna O'Mahony and I'm a first year PhD student at the University of Edinburgh. And today I'm going to be talking about factors which affect the evaluation of synthetic speech in context. And this was done with my co-authors, Pilar Oplustil-Gallegos, Catherine Lai, and Simon King. So as we know, TTS traditionally has been made for single utterances. And usually when we're generating long form TTS, we concatenate these isolated utterances together. But we also know that that's not how human language works, and we don't talk like that. In fact, how we talk is very context dependent, and how we realize our prosody is context dependent. And as TTS has become a lot better with regards to quality, a lot of research is now focusing on using contextual information to generate prosodic variability and also contextually appropriate prosody. And so what we should see is different realizations of prosody given a different context. But the question that we always come down to in TTS, of course, is how do we evaluate these kind of systems? So because we've usually dealt with isolated utterances, the evaluation paradigms that we have, such as mean opinion score, have also been developed for isolated utterances. And again, as I mentioned, we really need to come up with a unified approach to evaluate prosody because we need to be able to compare our systems to one another. So Clark and colleagues were the first to look at the mean opinion score and how we can use this to evaluate sentences in context. And what they wanted to look at was what is the effect of different contexts on the MOS score of a target utterance. So here, for example, we would have we would have 2 sequences of sentences, and we would want to know how the yellow sentence affects the rating of the blue sentence. So what they did is they presented target utterances to participants, and they wanted to know whether context had an effect. So in one condition, they presented no context, so they wanted to know the MOS score in isolation. In the second condition, they used natural speech as the context utterance. In the third condition, they used text, so no audio. And in the fourth condition, they used context unaware TTS. And it's important to note here that the TTS systems that they were using were not contextually aware. So these were just vanilla TTS where each utterance goes in on its own. And they found something quite interesting. They found that the MOS score for a target sentence was the highest when the preceding context was TTS. And again, this is quite surprising because if we think of isolated utterances generated and then concatenated together, we might assume that it wouldn't lead to an increase in MOS score. So this also surprised the authors, and they hypothesized that there might be some reasons why contextualized, when using TTS context, we get a higher mean opinion score. The first issue was that the instructions for single utterances were different to the instructions for the utterances in context. Specifically, in isolation, the utterances, they asked how natural the utterance sounded. Whereas when there was a context and target pair, they asked how appropriate the target was given the context. So this might have led to some issues. Secondly, they also hypothesized that when we have a single utterance and it's preceded by a context, the context often sets the scene for, we often have anaphoric reference in the target utterance, words like he, she, they, and it. And so that possibly when the context is given, we will see an increase in MOS score because we're able to understand the full sentence. But there were some other issues that they didn't approach in this study. So they only manipulated the contexts, which means we're actually still not sure whether the MOS paradigm is sensitive enough to within system prosodic differences. So what if we have a system that its baseline quality is always the same, but it can generate different renditions and we want to know which one is the best. So the question is also unclear if MOS is sensitive to that. So the goals of our studies today is one, to test whether the instructions actually have an effect on the MOS rating. So we'll look at that in experiment 1. In experiment 2, we wanted to look at the textual characteristics of the stimuli to see if these have an effect on the mean opinion score. And finally, in experiment 3, we wanted to see if the mean opinion score paradigm is actually suitable to distinguish between prosodically appropriate and inappropriate sentences or utterances. So for all of the experiments presented today, we used LJ speech, and we used DCTTS, an Edinburgh implementation of DCTTS called Ophelia, and everything was vocoded with wave RNN. In order to have more control of our stimuli, I generated context target pairs from Wikipedia facts. So we didn't want to use, so in the Clark paper, they used utterances from their held out utterances from the data they had. But we wanted to move beyond the LJ training data and have more control over our stimuli. So we created 55 context target pairs. And when the participants heard these pairs together, so not in isolation, we concatenated them into one audio file with 400 milliseconds of silence. So here you can see an example of a context and followed by a target. The general MOS task was just quite as you would expect. We used 1 to 5 scale with 0.5 increments. That's also following the Clark paper because we wanted to keep it as close as possible. We recruited US English native speakers and everything was online with headphones, and anyone who said they didn't have headphones was removed. The interface looked as follows for single sentences, as you would expect, but where they heard the sentence in context, the target sentence was presented in bold, and they were made aware of this in the instructions. So for experiment 1, we were interested in how the instructions might affect the mean opinion score. And so we had 3 conditions. The first condition contained 55 target isolated utterances. And here we wanted to know how natural that sounded. And this condition was really a baseline. What's the baseline isolated MOS score for these utterances that we're dealing with? In the second condition, the same target utterances were embedded in their context, a single context sentence, and the instructions read, how natural does the sentence sound given the first sentence? And then finally, in the third condition, we had the same target utterances, but we asked how appropriate the sentence sounds given the first sentence. So to the results, we found no significant difference in the naturalness conditions. So when we asked how natural something was in isolation versus in context, we didn't find a difference. However, following the Clark paper, what we also found was that there was a significant difference when the instructions differed. And so this tells us that asking how natural something is in context is not the same as how appropriate. And it also raised the question for us, what does this appropriateness rating actually mean? What are they taking into account? So in order to look at that, we decided to look first at textual characteristics. So in experiment 2, we wanted to look at the context dependence of the target sentence and see if this impacted the MOS rating. So we would hypothesize that if sentences sound better when they have a context sentence, then we should see differences between sentences that don't need context to be understood and sentences that do need context. So we had 2 conditions, with or without references, that needed to be disambiguated. And every subject heard the same, both conditions, but never the same sentence in both conditions. So here's an example. So we have the same sentence I presented earlier, but this time we had 2 versions. In the first version, we have anaphoric reference. And in the second, the referent is filled in, which means this is a standalone sentence. So what we found in the results was that there was no effect of context dependence when the utterances were presented in isolation. So they didn't prefer one or the other just because one had reference. And similarly, we also did not find that this made a difference when they got their context. Again, however, we do see this effect that in context with the appropriateness instructions that we see this boost in MOS score. So this seems to be a stable property across experiments. This doesn't, however, we can't conclude that text is not important in the appropriateness rating because all of the experimental stimuli were well-formed sentences in English. So probably a future experiment would be to look at maybe putting in some ungrammatical utterances or some semantically strange utterances. But importantly, what we wanted to know is this MOS paradigm really appropriate for prosodic variability? And especially when it comes from a single system where other factors such as general baseline naturalness will be the same. So for this experiment, the texts were the same as experiment 1 and 2. But what we wanted to do was to keep the context the same and modify the target utterances prosody. So we used DCTTS again. However, we used a modified training scheme, which was developed by Antti Sudi and colleagues at the University of Helsinki. They used continuous wavelet transform and used this to create prosodic labels which correspond to accents and boundaries. And what they did was they were able to mark up the input text to DCTTS with these boundary, accent and boundary labels. And what this means is during training, the model implicitly learns what these labels mean. And at synthesis time, we were able to adapt the labels for our stimuli in order to get different renditions. So we decided to create prosodically canonical and non-canonical target sentences. So we tried to make them quite different and one a lot more well-formed than the other one. And there's still both possible renditions, just one was slightly strange. So here's an example of a canonical and non-canonical form. And as you can see, there's some differences in, for example, the first one, we've changed the accenting pattern there. So I'll just play two samples for you. I hope you can hear them.
Storms have been named in the US since the 1700s. For the UK, it's a relatively new thing. The first one to receive a name in the UK was Storm Abigail in 2015. Storms have been named in the US since the 1700s. For the UK, it's a relatively new thing. The first one to receive a name in the UK was Storm Abigail in 2015.
So I hope you could all hear them. So the differences are most likely to be seen on the first one. So the second one is actually the canonical form where you wouldn't expect a large accent on a referent like 1 in this case. So on to the results of this experiment.
Storms have been named.
We found that in isolation, there was a significant difference between canonical and non-canonical realizations. So it also means we did correctly make a non-canonical form that was less well-formed. But interestingly, something that surprised us was that both the canonical and the non-canonical form received this boost in MOS score in context. So we wouldn't really have expected that because we created the canonical form to sound a lot better in context than the non-canonical form. So this was quite surprising. However, importantly for the study, we wanted to know, would the MOS paradigm be sensitive enough to basically decide which one you would want to pick, which one was the better rendition given the context. And we were still able to find a significant result, a significant difference between the canonical and the non-canonical form in context. So this does say there's some sensitivity. However, because our differences were quite stark between the canonical and non-canonical, it's unclear whether there would be, whether this would still be sensitive to subtle differences. So in conclusion, we found that instructions do affect MOS ratings. And so it's quite important that we always mention what kind of instructions we give to our participants when we're performing such experiments. We didn't find an effect of context dependency, but again, text could possibly still be a factor that they're taking into account with appropriateness. We found that the Moss paradigm is still sensitive to prosodic differences, but as you saw, both the canonical and non-canonical form were both rated highly in context, which we didn't expect. And as you probably also saw, the differences between those two in context was a lot smaller. And yeah, as I just mentioned, it's unclear whether subtle differences, often these systems that use context, when we're comparing them, the differences can be quite subtle. So it's unclear if that's really a good paradigm to use in that case. Maybe a preference test would be better. So some limitations on future work. Again, as you saw, it's unclear exactly what participants are taking into account under appropriateness. It's not context dependency, but they seem to be doing something that's more than prosody. So future work should probably manipulate the grammaticality of sentences, the semantic felicity of sentences, in order to see how much text has an impact on those ratings. We also would like to look at how the prosody of the context sentence can change the ratings of the target sentence. And finally, we'd like to move a bit beyond the mean opinion score, because as you saw, the differences are starting to get quite small, even when big effects could be there. So we would like to look at more implicit measurements of speech processing, such as reaction times, cognitive load, eye tracking, and that kind of thing. So that's the end. Thank you.
Good. Thank you very much. Right. So are there any questions? There's one question in actually multiple questions in chat window. Can you see that? The first one is from Geras, asking whether you look up TTS evaluations as like a whole up instead of just like a TTS isolations. And they said they found a strong correlation with overall user experience of the app with most performance. Do you have any comments on this?
We haven't at the moment because we weren't really looking at a use case at the moment, so we don't really have an app that we were using for user experience. But I think some work has been done on creating more, on embedding stuff into a more simulated use case to see if that would make a difference. So I think when we look at conversational speech, that's something we would definitely look into.
Second questions from Ayushi in chat window. If more than one TTS systems are tested, would the increase most be uniform across all of them?
I'm not sure. I mean, that's something we'd have to look into, but I think when we look at the canonical and non-canonical form, if you imagine that you had two systems and one of them was just producing these non-canonical forms, you would see somehow we did see this boost also in the kind of worse prosody. So I think because this seems to be a stable property, that would happen, but I guess it would really depend on the system. We'd have to look into that more.
Okay, so I saw that Gerald come closer to the microphones. I guess you have questions.
Yeah, thank you. I suppose that your DC TTS system is able to synthesize two sentences. No, it has been trained for large sentences. So what happens if you compare the synthesis? So you synthesize your context, the target separately, and it could be interesting to compare with the synthesis of the whole. So the encoder has the two sets of sentences. So are you planning to compare this? What do you expect?
I'm not sure I fully understand.
U-trans number 1, pause of 400 milliseconds, U-trans number 2, okay? and you have a different, okay, so DC, TDC, whatever. But if you input in the DC TTS uterance 1 plus uterance 2, so just the DC TTS is in fact synthesizing the pause, the dot, and so on, the full stop, and so on. So is that preferred or not?
So in general, these models tend to not do well with very long utterances. So there's definitely.
Okay, so take shorter sentences. No better. What do you expect? So
from the model, I expected to do quite badly, but we were focusing on more about how the evaluation works rather than trying to create good TTS in context. So the goal of this paper was not to create better contextualized TTS. It was to say, what happens if we have such systems, how can we evaluate them? So it was a bit more of a man in the middle or a woman in the middle kind of evaluation where I was manipulating the prosody with labels. So
your system is not aware that there was a preceding uterance.
No.
So it could be interesting to test if a system trained on larger span is able to restore, in fact, the coherence between the two utterances in terms of prosodic patterns, rhythmic patterns, and so on. No?
Yeah, yes. I mean, that's what I'm working on in my own PhD. This was just for evaluation, but yes, in general, this is yeah.
Okay. Thanks.
Good. So you have many questions in the chat window. From the cashier, so she said, do you think the most paradigm work when evaluating various TTS system where the listener have to make several distinct decisions without a difference?
I'm not sure, actually. Sorry.
Then maybe host, I don't know who is the host of this call, but could you unmute Rob Clark microphones, please? Because I think you'd be nice to have his questions verbally. Sorry, I don't know. We can do this spontaneous, but he's asking whether have you tried? Okay, good. We have him now. So Rob, could you ask himself? Could you ask your questions, please?
I mean, I can answer it anyway. Yeah. So that's definitely something I want to look at, because specifically I will be looking at question answering and answering in a felicitous way, and I'm working more on conversational speech. So this was more of an early study of looking at evaluation, but this is exactly the kind of thing that I will be focusing on in the future, on looking at the relationship between the question and the answer specifically. And so hopefully you'll see more papers on evaluation of conversational speech and these kind of phenomena.
Cool. Can you hear me now?
Yeah, I can hear you.
Okay, so I was going to say that the part of the reason we put appropriateness in was to distinguish between the sort of contextual cases where there were multiple ways of saying something, and one of them was the right way to say it in the given context, rather than to actually have it as in opposition to naturalness. We just wanted to know what the difference was. But it's good to see someone's carrying on with this type of work. We're very interested in following what you do.
Good, thank you very much. So the last questions from Wataru. So he's asking whether you try longer contexts, like 3 sentences rather than 1 sentence.
Yeah, so actually in Rob Clark's paper that we mentioned in the study, they also had other conditions where they did longer contexts. However, because we wanted to do quite a controlled experiment looking at multiple features, we wanted to first see if it worked with a single context utterance. But indeed, it would be interesting to look at longer form, and that's a whole other kettle of fish. But I guess I would refer you to Rob Clark's paper for looking at longer paragraphs for that.
Good, thank you very much. So yep, let's thank the speakers. Thank you very much. All right, so I forgot to say that, but if you want to speak for asking your questions, please press a button named Raise a Hand. The host can unmute your microphone, let you speak. Let's move on to the next paper. The second paper in this session is titled Non-Native English Lexicons Creations for Bilingual Speech Synthesis. And the presentation would be given by, yes, presentation is given by Alan.
Hello. Can you see my screen?
Yep. Yes, we can hear you. Also, we can see your slide. Please go ahead and start your presentations.
Yeah. Hello, everyone. Today, I'm going to talk about non-native English lexicon creation for bilingual speech synthesis. My name is Arun Baby. I'm a research scientist at Sapper Media Labs. At Sapper, we are trying to create mainly two products. One is a voice bot and other is a voice analytics bot. So let me start with the languages in India. In India, we have 22 official languages, which are written in 13 different scripts. We have 122 major languages and around 1,600 other languages. And Indian population, 22% are bilingual and 5% are trilingual. When I say 22%, that is almost like the population of United States. And in case of urban India, it's almost 44%. And the way Indians pronounce these English words are highly influenced by their native language. So this has this create a problem of having an Indian English lexicon separately, other than the CMU or deep dictionary. So main problem here is that we don't have an exhaustive dictionary available publicly for Indian English. And most of the systems still uses either the CMU dictionary or the deep dictionary, which are mainly targeted for US or the UK based speakers. And for Indian languages, we have a different label set, which is called common label set. Yeah, and there has been some work to develop some kind of lexicon previously. One of the main work was in ASR, where they have tried to merge different kind of phonemes so that the ASR could recognize much better. And in another approach, there was a transliteration-based approach where some manual effort was done on top of the dictionary correction. So the problem with these kind of approaches are these are manually intensive and hence not scalable. So in our approach, we are trying to figure out rules automatically from some set of words that are manually transliterated. So this is working for Indian languages, mostly because Indian languages follow phonemic orthography. In most of the, for our evaluation, we have done the evaluation in Hindi language, which is the most common language in India. Okay. Yeah, so let me explain the process here. So here, okay, we have identified 2K words which are mostly occurring by scraping the web, and we first figured out the corresponding equivalent transliteration for all those words. So once I have all those words, first we have to get 3 different kind of sequences. So first sequence is the letter sequence, where we just combine some set of letters and find some kind of sequence from that. For example, accord, the word accord, we have to split it into A, C, C, O, R, and D. This kind of sequence need to be formed. The second sequence is the CMU based sequence, where we use the CMU font set. We use a generally available parser, which is called G2PN, which basically convert the English word into corresponding CMU font set. And we are using a syllabifier on top of that. So for the accord, the syllable sequence will be R and chord, and the font sequence will be AH, KO, R, and D. Similar to that, as I mentioned earlier, we have something called a common label set, which is a font set developed for Indian languages. So from the transliterated word, this is accord written in Hindi, we are getting the corresponding CLS font set as well. Now the second task is we have to align all these things properly. So here, this accord, we are aligning with the CMU font set, CMU font sequence, then we are aligning with the CLS font set afterwards. So once this kind of alignment is done, we are manually analyzing all these triplets to figure out what kind of mistakes are happening. So once we have the set of triplets, we will figure out some kind of rules for this modification of phonemes. And with this thing, we can just either integrate into a parser, or we can manually correct our entire dictionary. So earlier I have shown you an alignment where we had equal number of phonemes with the equal number of English letter sequence. So here, this may not be the case always. For example, in the case of the word called, the number of phonemes is less compared to the letter sequence. So some kind of alignment we have to do to get the proper alignment. So we are using some kind of heuristics for this. For example, PH, CH, NG, SH, TH, ER, OW. These kind of letter sequences are always combined. All the double consonants are combined. Then AEIOU followed by AEIOUY. These kind of things are combined. Also for the alignment, we are using an LCS-based alignment. So here also some other extra heuristics that we used. For example, C and K, we know that the English letter C is directly mapped to K in the CME font set, which is also equivalent to small k in the CLS font set. So this kind of heuristics has been used when you are giving the alignment, when you're finding the proper alignment. So basically, this kind of equivalents have been considered as zero cost. So once I have all these triplet, so basically the letter sequence, the CME font sequence, and the CLS sequence, we are manually identifying some of the problems that are occurring here. For example, in all these cases, wherever O is, so this block shows the cases where A is going to AX in the CLS font set. So here you can see that whenever that AA is aligned with O, it's always going to AX. But similar to that here, A is aligning to A, but in this case it's going to AA. But we can see another case where A is going to AX also. So this set we are not considering a rule, but here since we could see that majority of the things are going into AX, we are considering this as a rule for correction. So we have identified some set of rules based on this thing. As I have explained before, O going to AA, we are almost always replacing it with AX. Similar to that, we have identified 5 other syllable-based rules, and there can be other kind of rules. For example, sequence rules, where some sequences, if we have an equivalent matching sequence in the CME font set, we can replace it with the CLS font set. So here, for example, ambulance is the English way of pronunciation. For the Indian way of pronunciation is ambulance. So those kind of things are corrected here using this sequence rule. Similar to that, we have prefix rules where the word automate, which is the US way of pronunciation, or the English way of pronunciation, whereas the Indian way is automate. So those kind of corrections are identified here, and we have formed rules based on that. Similar to that, the alertness, which is a suffix rule. So these kind of things are identified, and we have created some set of rules to correct the final parsing. Here, in this slide, I just want to show how many of the words in the CME dictionary are going through these rules and getting corrected. For example, all the syllable-based rule, around like 12% of the words are getting corrected. Sequence rule, it's very less, and prefix and suffix rules is a major chunk. So we have conducted experiments on Hindi TTS dataset. We have taken 9 hours of Hindi data and English data for the same main speaker. And so we have used Tachytron as the front end and parallel wave as the Pokora for all the experiments. We have 3 different models for testing. First model, in case of first model, all the English text, basically all the English words, we are using the CME font set. And for all the Hindi words, we are using the CLS font set. So here we have 39 unique CME font set fonts and 59 unique CLS fonts. In total, we have 98 fonts. So we are evaluating another model where we are reducing this font set as well. So wherever we could find a commonality between these 2 font sets, we just reduce that. In the third model, we have identified all these rules. So we'll put the word through all these rules, then it will be reduced to the reduced font set. So yeah, here, this is the results of all our evaluation. So first one is the comparison of model 1 versus model 2. Here, the only change we have done is we have moved to a reduced font set. So this is the result of a preference text. So in case of evaluation 1, you can see that the model 2 is performing worse compared to the model 1, which was having more fonts. Yeah. So here the problem mainly is that when we are directly mapping across this CMU and CLS font set, there can be multiple confusions. So this is evident because the results are showing that the performance is degrading. So I'm just moving to evaluation 3, where we are comparing the model 1 with the model 3. So model 3 is our proposed model. So here you can see that in all cases, we are seeing around a 6% improvement, 6% absolute improvement. So there are 3 different cases here. The dict one, where this is tested on seen words. So 200 words are taken from the TTS training data itself, and we have synthesized that. So there itself, we could see some improvement. Then we have taken words which are not part of the training data, but which are part of the CMU dictionary and synthesized. So here, 200 random words are chosen, in which these rules are getting applied and the phonetic sequence are getting corrected. So there we could see a 6% improvement. And another test we have done where we are checking out of rules. So basically, the words which are part of CMU dictionary, which didn't go through this rule, a subset of words have been chosen, and a subset of words have been chosen, and we have done the evaluation. There also you could see the similar percentage of improvement. So the reason here could be because since the rules are correcting so many of these confusions in the training data, the phonetic models are getting much better. That is why for the other one also, the out of rules also, it's getting improved. Performance is getting improved. So all the audio samples we have kept in this link, which is available in the paper as well. So it's a conclusion, we can say that around 35% of the 130K words in CMU dictionary is being corrected using this rule. That means a major chunk is corrected. Even though this set of rules that we have identified is not an exhaustive set of rules. And here the minimal transliteration effort only is needed. We have identified only 2K most commonly used English words. And this can be scalable to any of the phonetic language. And here we could see a 6% absolute improvement in case of the preference text. Thank you.
Thank you very much. Any questions, comments from audience? If you want to say your questions directly, please press raise the hand buttons. Yeah, okay. So there's one question in your chat window. Did you consider using a British accent lexicons instead of
yes,
American
we have a dictionary which is basically based on the British accent. There also we could see many of the errors compared to the Indian way of pronunciation. That's why we went ahead with this kind of approach, where correcting some kind of or creating some kind of rules which can be used across any of the passes.
I see. Yeah, another question from Javier. So could you comment on the accent of the voice speaking English for each one of the methods?
So the dataset that we have used is neutral voice, which is almost kind of the news reading, and plus a bit of storytelling.
Right. So other questions from Vivian. Does your models handle lexical stress at all? If no, it is not
Indian languages, we are not stress time. So basically, we are not considering the stress as such. Whenever we are converting, we are just taking the base one, not the stressed one.
I also have one question for your papers. I wonder how you train G2P after you define lexicons. Did you also define your G2P models, or did you use G2P models built for English as is, or how did you handle G2P part?
So the G2P we are still using is the G2PN, which is the publicly available one. We are just putting all these rules on top of this thing to get this corrected. We are not training any extra G2P model on top of this.
I see. Do you think it's worth fine-tuning your G2P using new lexicon somehow?
Yeah, we could try that, but for now, this works for our purposes.
Okay. Are there any questions?
There is one more question from Gábor. Yes, but was a method one more or method one more Indian accent or less? No, I didn't exactly get this question. Gábor.
Javier, do you want to clarify your questions? We could unmute your microphone if you want. Okay, he still prefers typing.
The data set that we are using is from an Indian English speaker. He's a Hindi speaker who is a bilingual. So the data is collected from a native Hindi speaker.
I see.
So this sounds, finally the synthesis sounds more like a Indian English, not like a native English, which is what we want when we are going for an Indian audience.
I have one conceptual questions. So when we need to handle those kind of non-native English lexicons, it only depends on the fluency of the speaker. So how do you plan to handle such a difference of the skills or English fluency of L2 speakers?
So this is mostly applied for the TTS part. So even if that person, the actual person who is not a fluent guy, still we can make use of these rules to have a fluent pronunciation for him or her. There is one more on that acceptance of the target on. Yes, so this is mainly for the Indian audience. That's why we want the lexicon to mimic the Indian way of pronunciation.
Okay, so I think we have a few minutes, so maybe I will ask another aspect. Do you think we could use kind of like a self-supervised approach instead of adding lexicon somehow to create dictionary indexes automatically somehow?
Yeah, it depends. So if you're going for a phonetic-based TTS, that may not be ideal, but in case of a character-based or something like that, we could use some other self-supervised or some kind of approaches. And another problem could be getting enough data for all these things. And Indian languages are supposed to be the low resource languages.
Yeah, that's true. Yeah. Okay, so are there any questions? Also from the room? Maybe not. Okay, then let's thank the speakers. So thank you very much for your presentations. Okay, then let's move on to the next presentations, which is titles Cross-Lingual Transfer or Phonological Futures for Low Resource Speech Synthesis. And the presentation will be given by Dan from University of Edinburgh.
Yep. Hello. Can you hear me okay?
Yes, yes, I can.
Cool. Let me share my screen. Okay, can we see that?
Yes.
And I'll just check the audio plays.
Ich musste meine Zuflucht zu den Gestirnen nehmen und euer Horoskop stellen, das Geheimnis zu lösen.
Could you hear that okay?
We had a few mix audio, I think, but at least we had audio, so it should be okay. So please go ahead and start your presentation.
Okay. Cool. Okay, yeah, so my name's Dan, and I'm going to talk through our work on cross-lingual transfer of phonological features for low-resource speech synthesis. So basically this paper is trying to approach some of the data challenges in TTS. So if we think about recent neural approaches, typically these are trained using tens of hours of audio and corresponding text transcripts. These high-quality recordings can be expensive to gather, and so this high-quality TTS has been limited generally to a small proportion of the world's 7,000 languages. One way we might want to get around these data challenges is by taking a transfer learning approach. So training a source model for some language where we do have plenty of data available, for example, English, and then fine-tuning using a small amount of annotated data from our target language. And the question we wanted to ask here was, can we make this process more efficient somehow through choice of input representation? So rather than using characters or phoneme symbols, as are often used for TTS, we use this phonological feature vector representation. So basically what we're doing is converting these atomic phoneme symbols, IPA symbols, into vectors of binary distinctive phonological features, where each individual feature specifies something like a position of articulators in the vocal tract, a degree of closure at some specified position, whether the vocal folds are vibrating, and so on. How can this help us? By using this kind of representation, this kind of reveals relationships between sounds that are not apparent if you're only working with these atomic phone symbols. So, you know, I have a series of things here. I've got these IPA symbols, the X and the K, and I can tell you those are, you know, this is a voiceless velar fricative, this is a voiceless velar plosive, and maybe you get some idea, okay, these are quite similar sounds, closely related in terms of their articulation. But, you know, if we convert these to indices in some phone embedding table, that information isn't available explicitly to our model. But if we convert these beforehand to phonological feature vectors, so here we have a set of 25 binary features. The representations for these two phones are identical, except for the specification of a single feature, which is this continuant feature, which you know, basically is our toggle for plosive versus fricative consonant. And this kind of representation also helps to set up the transfer learning fine-tuning kind of procedure that we want to do. So if you're working with a phoneme-based system, and you want to fine-tune something in a target language with a different phoneme inventory compared to your source language, you know, we're going to be working with English and German. So this velar fricative is the sound at the end of a German word like Bach, which we don't have, at least natively in my variety of English. So, you know, when we start the fine tuning, we have to make a decision: are we just going to randomly initialize our phoneme embedding for this, or maybe we make some hard decision about copying parameters from the nearest equivalent English phone, which would be this velar plosive. But you know, either way, you kind of have to, you know, that's something you have to do and fiddle around with in the architecture of your model. But if we're using this phonological feature vector representation, you know, we select a set of features that account for all of the contrasts of interest in our languages. So we can say this is a universal input vocabulary for our purposes, and really just compose the representations for these previously unseen phones from stuff that we already know about. So things like velar consonants and other types of fricatives, to give us a better starting point for fine-tuning in phonological feature-based systems. So just a brief survey of some previous work that's used these phonological feature inputs. So these Gutkin and colleagues have looked at multilingual training using some combination of phoneme and phonological feature inputs, and they found you know, some improvements in low resource cases in naturalness ratings for low resource languages, especially compared to training from scratch with very little data. And then this Steibetal paper also used phonological feature inputs, slightly different formulation from ours, but similar in principle, for zero-shot synthesis in code switch text. So if you have some German words, for example, embedded inside an English utterance, you can just feed through the phonological feature vectors for those target words without worrying about doing any fine-tuning at all. So the data models that we're working with here, as I said, we're looking at this kind of transfer learning setup. So we have an English base model trained using 14 hours of audiobook recordings from a single female speaker. And then we train a series of German models from a different single speaker. We have one trained using 4 hours of data from scratch. So this is kind of not looking at any of the English data. One using the same 4 hours, fine-tuning the English base model. And then one fine-tuning the English model using just 15 minutes of the German data. And for each of these systems, we train two versions, one using phoneme inputs and one using phonological feature inputs. As for what these models are, so it's a Tachytron 2 architecture based on the Mozilla TTS implementation for acoustic feature prediction, and then the audio generation is done with a parallel waveGAN vocoder trained just on the, well, trained using the 14 hours of English data. Okay, so I want to start by looking at some of the representations learned by these models. So we're going to look at a few of these UMAP projections of representations pulled out of the encoder. This particular figure is, showing the phoneme labels for representations learned through phonological feature inputs in the German model trained on 4 hours of data from scratch. And I'd just like to point out that these input embeddings kind of reflect some phonetic relationships that we that we know about, and I think it's quite reassuring to see that the models are learning something that we can interpret on a linguistic basis. So the major distinction here is between vowels and consonants. We've got vocalic segments on the left and consonants on the right. And if we look at this kind of consonant space, there are distinct classes of consonants in here that are also clustered together or grouped together separately. So we've got all our fricatives on the right-hand side here, plosives in the middle, and nasals on the left. And in cases where there are voiced and unvoiced consonant pairs at the same place of articulation, these are also close together. So this perm, bur, turn, der, and the fricatives, fern, ver, and so on. So I think this is kind of a nice starting point for looking at these embedding plots. Now, moving on, we'll look at the embeddings learned by the phoneme-based systems. So I've got three systems here. On the left-hand side, the English base model. In the middle is the German model, fine-tuned with 4 hours of data. And on the right is the German model trained from scratch. In all of these, the phones which are only observed in the German data are marked by circular outlines. And because this is a phoneme-based model, at the beginning of the fine-tuning, we initialize the representations for those German-specific phones using the nearest equivalent English phone, basically according to phonological feature distance. And those are marked here with the square outlines. And I'm going to focus on 2 specific phones here, just for purpose of illustration. So these 2 German-specific fricatives. So there's the velar that we saw before, and there's the palatal one, which is at the end of the word ich. And I think these particular phones kind of distribute differently across these 2 German models. So when we train from scratch, because these are quite similar sounds, they lie quite closely together, and they're nearby all of the other fricatives observed in the German data. Whereas in the case where we've fine-tuned this German model from the English source model, for these phones and in general, the representations don't move very far from where they're from the phones, the English phones from which they were initialized. So that has the result of splitting up these phones here in this fine-tuned case, and you see it kind of muddies things up a bit here as well. We've got some plosives kind of pulled in, and it's just not quite as clean as before. Whereas if we move on to the phonological feature vector-based systems, I think the picture here, I've got the same array of models. I think the picture here is much more consistent across the different training scenarios. So if we look at these particular phones again and the scratch trained system, they're close together, they're with the other fricatives. In fine-tuning, similar kind of story. And then we can also do this neat trick, because this is, we've got a shared input vocabulary here. We just do a zero-shot embedding using the parameters of the English model. So this is exactly as it was at the end of the base model training. Has never seen any German data, never seen any of these phones. But we compose those phonological feature vectors and embed them here, and they kind of end up more or less where you would expect them to. And I think this kind of suggests that maybe if you use these phonological feature vectors, it's kind of gives you maybe a more principled method for sharing information in this cross-lingual transfer learning. Now, if we just look briefly at how this translates to listening test results, we did a Mushra-style listening test with native German speakers. If we look first at these two bars here are the Scratch-trained German systems, trained on 4 hours of German. And we see here a small but significant improvement in subjective naturalness ratings when using phonological features compared to phoneme inputs. And if we compare these two systems to those fine-tuned using only 15 minutes of German, that's these two here, for each of these kind of pairwise comparisons, there's no significant difference between these 15-minute fine-tuned systems and the 4-hour Scratch-trained ones, which suggests that this fine-tuning approach is useful even with very limited target language data. And I'll take this opportunity to play some samples. So I've got here a German sentence with the German-specific phones highlighted in red. I'll play the reference first.
Ich musste meine Zuflucht zu den Gestirnen nehmen und euer Horoskop stellen, das Geheimnis zu lösen.
Then this is going to try and load first, and I'll play it again. The phoneme-based system trained from scratch on 4 hours of German.
Ich musste meine Zuflucht zu den Gestirnen nehmen und euer Horoskop stellen, das Geheimnis zu lösen.
I think you probably heard there some kind of we chewed this sequence of phones up a little bit. I think this is kind of an attention problem, given the limited data and the Tactron 2 architecture that we're using. If we listen now to the phone-based system, fine-tuned using 15 minutes, that problem kind of goes away. I think a major benefit of the fine-tuning for the Tactron is, you get the benefit of the alignments you learned on a large amount of previous data.
Ich musste meine Zuflucht zu den Gestirnen nehmen und euer Horoskop stellen, das Geheimnis zu lösen.
This also wasn't an issue for the phonological feature-based system trained from scratch.
Ich musste meine Zuflucht zu den Gestirnen nehmen und euer Horoskop stellen, das Geheimnis zu lösen.
Although I don't have a particular explanation for that. And then just to round out, I'll play the 15-minute fine-tuned phonological feature system.
Ich musste meine Zuflucht zu den Gestirnen nehmen und euer Horoskop stellen, das Geheimnis zu lösen.
Okay, so just to summarize, we looked at using phonological feature vector inputs for low resource TTS. This has, besides anything else, I think practical benefits for kind of fine-tuning setups over manual phone mapping in a phoneme-based system because of this shared input vocabulary. We found apparently more consistent cross-lingual phone representations learned using the phonological features, and a significant improvement in subjective naturalness ratings for low resource training using the phonological features over phonemes if you're training from scratch. Next steps, we only looked at 2 quite closely related languages here. We want to extend this to multiple, more phonetically diverse set of languages in future work, and also look at some other methods for encouraging more and better information sharing in these multilingual models. Yeah, so that's everything. Thanks for your attention, and look forward to answering any questions.
Good, thank you very much. Are there any questions or comments?
Okay, I see the chat.
Yeah, there's one question from Javier. Did you consider training jointly with English data and all available German data before fine-tuning to the German data?
Right. No, not in this particular case. I think this kind of multilingual training setup is something that I will look at in kind of the next steps, but didn't think to do it in this case.
Another questions from, sorry, I cannot pronounce the name correctly, Robisa. For more diverse languages, do you think it could be useful to also have phonetic features depending on the language pair you're working with?
Yeah, interesting. If the phone pair is contrastive in the source language, but not in the target language. Right. Yeah. Aspiration. That's a nice point. Yes, I think this could be useful. If nothing else, because if you're working with phonetic features, you can have more fine-grained control of those things. I think I mean, you could, if you're using IPA input symbols, you can include diacritics like this for aspiration, if you like. But yeah, I think that's definitely something to think about.
Are there any questions? I also have one questions for your papers. How do you handle lexical stress and so on? Did you ignore those kind of informations, or did you include that as an additional input for your models?
Right. Yeah. In this particular work, I ignored that, although I did have it available for the in the lexicons, and I think I will in the lexicons that I'm using for future work. So I will probably include it. I think it makes. I think it would be very straightforward to include it as an additional feature in the phonological feature vector inputs, for example.
Yep. I also have another questions for your slide, page 9, if I remember correctly. You have system P something, F something, also with P with different numbers. It was not clear for me which system corresponds to which. So maybe could you turn on desktop sharing and quickly explain how to interpret?
Yeah, sorry. Yes. Yeah. The P is phoneme inputs. F is phonological features. Then we have the amount of German data, so 4 hours or 15 minutes. And the FT here is fine-tuning.
Okay.
Yeah. Yeah.
Good. There's one more questions from Javier. Did you try to play with phonological feature to generate unseen sound?
Yes, informally, a little bit. So this is kind of the zero shot synthesis that the Steibtal paper did, and I kind of played around with it as a initial proof of concept. I got slightly worse results than they did with their, which possibly was, I haven't yet worked out if it's because of the data we were using or the difference in the phonological feature representation. That was for like synthesizing the velar fricative unseen. That tended just to sound like a plosive. But I think for vowels, it was kind of better. So, German has a few kind of front rounded vowels that English doesn't have. And I think those were able to get closer to those German vowel qualities unseen. Yes.
The next questions from Geras. Actually, he has a microphone, so he may explain his questions to you. But he said whether you have built HMM synthesizer with same amount of data. I think he's probably asking like a 15 minutes case, HMM synthesizer can be built from such a small amount of data. So yeah, I think that would be his questions.
Right. No, I have not tried that. That could be interesting to try.
I have another quick questions. So you use a single speaker in English, but probably it'll be much better if you use multiple speakers in many languages.
Yep.
Have you tried such a scale up experiments?
No, again, this is the next step. So I think the kind of the corpus that I'm eyeing up for this is for scaling up is global phone, which I guess doesn't have English in, but I guess I can like add VCTK to global phone or something. But yes, it's a good point, and I hope that it would make things more robust as well.
Yep. The final questions from Adriana. Did you check if the 15-minute German data contain all the phones, or was it randomly chosen?
Yes, it did contain all of the phones. There's a bit more detail, there's any detail at all on this in the paper. I didn't go over it in the talk. So we kind of sampled the 15 minutes to try and not completely maximize, but increase the representation of the German specific phones. And they were all present.
Okay. So are there any questions from the rooms in Hungary? I don't know. I cannot see so clearly, but probably not. Okay, then yeah, I think that's it. Thank you very much for your presentations.
All right, thank you.
And let's move on to the next paper in these sessions. Sorry, please check me the titles. The next title of the next paper is Mind Your P's and the K's, comparing obstruents across the TTS policies with a challenge 2013, and the presentation will be done by Ayushi. Sorry for my bad pronunciation.
Thank you so much for the introduction. Can you see my screen?
Yes.
And can you hear me?
Yes, I can hear you.
Okay, so hello everyone, and welcome to the presentation of our work, Mind Your Pers and Curs. My name is Ayushi, and my advisors are Dr. Sebastian Lemaguer and Professors Julie Carson-Bernson and Naomi Hart. Speech synthesis evaluation means evaluating synthesized speech on the basis of its perceivable attributes. In this field, subjective evaluation using MOS-based scores is considered the most reliable method. However, some limitations of MOS, such as its lab-controlled settings or the lack of understanding of user-specific needs, have been noted in the literature. Also, complete reliance on subjective listening tests is quite expensive. At the same time, diagnostic limitations of MOS have been identified. That number on the MOS scale can mean anything from segmental distortion to prosodic flatness, even to background noise. In light of these issues, some research groups have approached embedding the evaluation in real-world settings or using automatic measurements to evaluate synthetic speech. Some examples are listed on your left. On the other hand, some research groups have identified that using behavioral or physiological measurements may help us understand user experience without tapping into the conscious decision-making process of the users. The examples of these are listed on your right. While each of these methods have their merit, we don't yet know what exactly are the physical features of the speech signal that a listener uses to make a decision about synthetic speech. What could have possibly changed in the signal for a listener to perceive it and say it doesn't sound natural or pleasant enough and assign it a low or a high Mohs score? A clear understanding of these features and in what capacity do they contribute to attributes like naturalness till today remains unclear. The analysis of this type of relationship is really important, both from the point of view of speech technology and that of speech sciences. From the speech technology point of view, we believe that this can complement subjective evaluations, providing information that can help us diagnose the Mohs score better. From the speech science point of view, different TTS systems can serve as good computational models of speech production. You will see in the future discussions that we have approached this using basic corpus phonetics techniques, while still remaining in the realm of traditional subjective evaluation methods. Now, let me draw your attention to the field of acoustic phonetics, where relationships between acoustic measurements and meaningful perception of languages take center stage. First of all, contrastive features in speech perception are those acoustic differences in the signal that contribute to meaning. For example, on your right, you see two images. These are obstruent consonants b and p. The presence of the low frequency energy region in the b and the absence of it in the p plays a crucial role in the perception of their difference. So in this research, we are drawing on the contrastive features such as these because they encode rich and descriptive information about the characteristics of phonemes in a language. Analyzing TTS systems based on these contrastive features can not only give us a set of features for analysis, but it can also provide guided theoretical direction when we compare their behavior across systems. For the purpose of this evaluation, we have chosen the contrastive features of obstruent consonants. They're a major phonological class covering 2/3 to 3/4 of consonantal population. Like the figure on your right shows, stops are produced with a complete obstruction of airflow released with a burst. Fricatives are produced using a partial one released in high velocity airflow. Affricates combine these two motions, start with completely obstructing the airflow and then release it like a fricative. These production characteristics give them a variety of acoustic consequences that are not possible to study or analyze in any other speech segments. Now, how does a text-to-speech system analyze these very special characteristics? How does it differ from the other one or from the natural voice? So this brings us to our research questions. Can we compare acoustic phonetic measurements of obstruent consonants across different TTS techniques? Can we identify those features which contribute most to the perceived naturalness? Do they do so in specific contexts? If so, then in what way can these results help us understand about techniques in speech synthesis? Now we come to the series of slides where we will describe the data set that we used and the procedure for phonemic and subphonemic alignments. The Blizzard 2013 dataset comes from the annually held Blizzard Challenge Series. The dataset comes with 100 parallel sentences submitted by 10 participating teams. The parallel nature gives us the advantage that the difference we observe are not biased by the proportion of consonants in one set of sentences versus another. The dataset also provides a good variety of TTS techniques with 5 systems representing HMM, 3 unit selection, and 2 for hybrid systems. A single speaker data set helps with controlling for additional sources of variation. Finally, Mohs scores are available with each system per sentence. On the right, you can see the ranking of systems based on naturalness and similarity. Hybrid systems, shown in red, rank the highest in naturalness with a mix of unit selection and HMM systems in the middle, shown in blue and purple, and predominantly HMM systems bringing up the rear. Here we can see the frequency distribution of the different phonemes in the corpus. This exact distribution is mirrored in each of the system submissions. As we can see, except for the post-alveolar fricative zh, we have a sizable distribution of each of the phoneme types across both the voicing categories. This slide explains the complete temporal alignment procedure of phonemic and subphonemic boundaries. In the interest of time, we will not go into the full implementation details. What is important to note here is that the phonemic boundaries for all the consonants were given by Montreal forced aligner. Then, since affricates and stops follow a silent region before their release, this silence had to be separated out. You can see the separation in the image displayed. Hence, only stops and affricates were given subphonemic boundaries using a semi-automatic procedure. Now we come to the experimental setup where we will describe the grouping of the systems, the features extracted, and the statistical model. This slide describes the feature set that we have extracted from obstruent consonants across each system. The feature extraction closely follows the seminal work of Dr. Aled Youngman and Dr. Charles Redman, whose doctoral work presents a very recent and updated compilation on the behavior of obstruents in English. Over several decades, these cues have been evaluated for their acoustic phonetic understanding of obstruent consonants, studied particularly for their contrastive properties. Feature extraction is during the durational, amplitudinal, and spectral cues, and the specifics of those features are listed. Okay, here we will discuss the grouping strategy of different systems. Let's first look at the figure on the right. You have already seen the top bar chart in a previous slide. These are simply the rankings on naturalness based on the Mohs score as a result of the subjective listening test. The bottom bar chart first categorizes similarly ranked systems into 4 different groups. R1 has systems that received Mohs scores between 3 to 4, R2 between 2 to 3, R3 between 1 and 2, and R4 close to 1. Then these groups were further subdivided by the TTS technique or system family that was used. This gave us 6 final groups. The need for doing this was to control for family dependent variation so that quality differences may be compared in a more targeted fashion. Okay, finally, we come to the statistical model. A linear mixed effects regression model calculates the relationship between the dependent variable and the predicted variable. In experiment 1, the purpose was to explore group differences between system groups of the same family, but different ranks. In experiment 2, the purpose was to explore individual differences between systems of the same family and the same rank. So for experiment 1, control for system family, only compare quality. Second experiment, control for family and quality, only compare individual system differences. The groups under comparison were HMM R2 versus R3 and UNS R2 versus R3, and the individual systems are listed on your right. Now, these are the model equations that were passed to the linear mixed effects model. A change in feature value can be attributed to the system group or the individual system, depending on the experiment. Now here, it must be carefully noted that the feature value calculated for the natural voice was considered the reference point or the intercept in each case. The deviation from this voice was the comparative metric across which different behaviors of groups were recorded. Okay, so now let's summarize it diagrammatically. First, we assign a sub-phonemic boundary or continue with phonemic boundaries depending on the manner of articulation of the obstruent. Then we extract a list of features and pass them through an Elmer model, with feature as the dependent variable and systems as the independent variable. Here, the feature that is considered most contributive is the one that shows maximum separation between these groups or individual systems, whatever is the experiment, and it does so across all or most of these manners of articulation. Okay. So now we have come to the results and discussion section. Here, before we begin, I want to introduce the color scheme that will help you interpret our results better. You will see 3 types of effects in our results. First is no difference from natural, then is significantly different from natural, and then third is also significantly different from natural, but with greater magnitude. So a difference like this means group 1 is not different from natural, but group 2 is significantly different from natural. Now this difference can be in either direction, either an increase in the feature value or a decrease. And now this type of difference means group 1 and group 2 both show significant difference in natural, but blue shows which group has a greater magnitude of difference. For example, in the case of amplitude, both 5 decibel and 10 decibels are differences, but 10 decibel is a larger difference. So that would be shown in blue. Okay, so let's begin with experiment 1. To begin with, we see the results of experiment 1 when we are comparing high scoring R2 versus low scoring R3 HMM groups. The features found most contrastive are RMS amplitude, peak amplitude, and spectral tilt. As you can see on your left, HMM R2 does not show significant differences from the natural voice in terms of RMS amplitude and in most cases of the peak amplitude. However, HMM R3 shows a lowering of amplitude in most of the contexts. In the third row, we see an important feature, spectral tilt, which shows no or moderate difference from natural in HMM R2, but a significant increase in HMM R3 in all the cases. Continuing in the vein of the previous slides, we are now presenting R2 versus R3 in unit selection systems. The features found most contrastive were consonant duration, noise duration, and spectral tilt. Spectral tilt once again. First thing interesting to note here is that all unit selections shorten the duration. They behave like a family. And second, as opposed to the observation in HMM systems, unit selection systems reduce the tilt. Now, the effect of the first feature, that is shortening the duration, is stronger in R2 systems, and the spectral tilt reduction is stronger in R3 systems, especially for affricates and fricatives. Okay, this brings us to the second experiment, where we have controlled for quality and system family, rank and system family, and we are looking at the individual differences between systems. So here we can see that while the best performing system M does not differ very significantly from the natural speech, the comparatively lesser scoring hybrid system K does differ in three important aspects: RMS amplitude, peak frequency, and once again, spectral tilt. Obstruents in K are louder, have a higher peak frequency, and show an increase in spectral tilt. Okay, and last, we look at features that show individual differences between unit selection systems of R2. Once again, we see little to no deviation from the natural voice in the best performing system L, except that peak frequency is lowered in some contexts. But overall, obstruents in N are softer and show reduction in spectral tilt. So this brings us to some of our conclusions. We have found that contrastive features of obstruent consonants can be used to identify differences based on naturalness in system groups and individual systems. These help us provide diagnostic insights into MOS, and the system behavior can now be correlated with MOS. Spectral tilt was found to be the most informative. HMM systems as well as hybrid systems show increased spectral tilt, indicating tendency towards high frequency concentrations of energy. This also indicates involvement of HMM-based spectral modeling procedure. Now, some of our long-term goals are extension of the Blizzard Challenge 2013 to include neural synthetic voices. And in terms of features, we want to do a closer analysis of obstruents and expand feature collection in feature extraction into other phonological classes, such as sonorants, vowels, and suprasegmentals, and so on. Thank you for listening. Sorry, I can't hear you.
Sorry, I muted my microphone. Sorry about that. Thank you very much for your presentations. Are there any questions or comments from the audience? Yes, actually, it's quite interesting to analyze the meaning or interpretations of the Morse code, because there's many ways to annotate or to provide the subjective code, and sometimes it's not easy to the messages behind. So, do you think we could combine this kind of analysis for interpretability, also most predictions to do explainable most predictions in the futures?
Thank you for the question. Yes, that would be one of the goals, actually, to make sure that a large enough set of features are collected. And together, all of only one phonological class is under consideration now, but all of them can show individual contribution and definitely make the MOS more diagnostic, at least in terms of acoustic phonetic properties of the consonants and vowels. And also, since we know more about the production characteristics of consonants and vowels in human language, we should be able to see what remains recreated or how much can get preserved in the different types of techniques of synthetic systems. So yeah, definitely.
Yeah, so we need to have both of the most annotations also some like reasons or some analysis of the why the subject provides a score. But yeah, if such a data is available, yeah, it might be possible to have such a explainable most predictors. Are there any questions or comments from audience? So Gerald has one question.
Thank you very much. How to say, the quality of the phonetic features depends on, even in natural speech, depends on very different factors, word predictability, position in the discourse. And when you in fact, you judge the position in the utterance also make a difference. When we were doing concatenative speech synthesis, we weight more concatenation scores at the end because it's preponderant in the judgment. So it's very difficult, in fact, to relate a quality of objective quality of the discriminative features and more score. So yeah, it's perhaps you could be interesting, in fact, to extract I don't know, the syllable and really to conduct another perceptual experiment, judging the quality without context. No, what do you think?
Yeah, so yeah, there
are too many contextual information in the global judgment.
Right, there is two parts to this answer. The first would be that right now we are looking at the general trends of the obstruent consonants, and you're absolutely right that positional variation between their presence can make a lot of difference, especially in the prediction characteristics that we see. That would be the very next step. Immediately, like what we want to do immediately now is to separate these contexts into CV, that is pre-vocalic, post-vocalic, intervocalic, and also clusters. And we want to see what is happening in each of the systems and what is the case. And that would be right now we want, since this is one of the first times we're doing this, we just wanted to make sure that general trends are showing something. Okay, and in terms of, yeah, so that is the very next level of investigation. Yeah.
Thank you very much.
Thank you.
Good. So there's one question from Rob Clark. Spectrum tilt appear to be quite important here. It's not something we tend to explicitly pay attention to in TTS because there's no explicit modeling for that. Any thought how we getting wrong?
Yeah, thank you for the question. Thanks. So right. So when we were looking at the second experiment, that is individual systems comparison, we found that hybrid systems, M versus K, K shows an increase in spectral tilt, and we found what was we went through the description of the system, and we found that the HMM system, sorry, the hybrid system K versus hybrid system M both have a spectral modeling that use the HMM for doing that. So they have the HMM based spectral modeling step. And in one of the systems, the two types of features are modeled using two different HMMs. One is spectral, so F0 is modeled on a separate separate HMM, and MFCC are modeled on a separate HMM. But in one system, which was found to increase the spectral tilt, that is system K, was reported to have to use the same HMM system for both. So this was the key difference that we found in the spectral feature modeling procedure, and we believe that right now it's still in the hypothesis phase. We believe that there are insights to be drawn between the observed production characteristics and the system design. And that's something we really want to explore more. And I think we'll definitely do that more. Thank you for the question.
Thank you very much for your presentations.
Thank you.
And let's move on to the final paper in this session. Improving polyglot species through merge task and adversarial learning. And the joint work of Edinburgh and sorry, I haven't checked affiliations, Facebook, and presentation will be given by Jason.
Thank you for the introduction. Can I just verify if you guys can hear some of the audio here? One second.
We could hear, but it's pretty quiet. Is it possible to make it louder?
Yeah, so this work on multilingual TTS was done whilst I was interning at Facebook, and it was done in collaboration with Jilong, Prabhav, Andrew, Tilo, and Ching. And yeah, this is a brief overview. So I'll be talking about multilingual TTS, the model that we've built, and some experiments. And so what exactly do we define as polyglot multilingual TTS? Really, it's just multilingual TTS. And our goal here is to, in any voice, synthesize in multiple languages, or even in any languages. And why is this? Well, there's a few reasons. One reason is that we want to maintain consistent voice identities when we're doing applications such as code switching or speech-to-speech translation. And I think another thing that the Facebook TTS team is interested in is sharing some of the voices from higher resource languages to lower resource languages, where you might not have many speakers in their training data sets. So what does a typical training data look like for multilingual systems? Well, in like the past decade or 2 decades, they would usually use data from bilingual speakers or multilingual speakers. So, you have a person who can speak natively in multiple languages. And then, multilingual systems can be built in several ways. So like some of the older approaches represented speaker and language transformations as sequential. And then newer like Tachytron 2 based approaches would just include speaker and language as conditioning features. And this is an approach that our model uses as well. But a lot of these models, although they can do multilingual TTS relatively well, they fundamentally use multilingual data. But this multilingual data is actually quite rare, right? Because it's quite hard to find people who can speak natively in 2 languages or even 3 languages. And then for a lot of language pairs, you just won't be able to find, speakers for them, especially not going to English. And so the alternative is to use monolingual speakers. So I think the previous Google paper, I think published 2 years ago, looked into doing this, and they use some approaches where they're trying to remove speaker information from the text encodings. And these models kind of perform quite well, especially when you have many speakers, many monolingual speakers. But when you kind of reduce the number of monolingual speakers, because there's a high correlation between the speaker and language ID, because if you know the speaker, and there's only one speaker for that language, you would know exactly what language it is. These models tend to kind of entangle the speaker and language features during training. And so when you try to do inference from them, they can exhibit some like phonetic mispronunciations, or if you're doing code switching, when you change between languages, you also change the speaker identities. And so like when we try to use monolingual data or data from monolingual speakers, and we don't have many speakers per language, this kind of presents some modeling challenges. And so the key goal of our work is to focus on this kind of very data sparse problem where you only have one speaker per language and each speaker is only monolingual. And, you know, if you were to train traditional models on these kind of data problem, then they kind of exhibit these problems. So in this work, we tried two different approaches to try and tackle this data problem. So we tried multitask learning and adversarial training, and I'll go into a little bit more detail in a second. So an overview of our model. So the model is a sequence-to-sequence acoustic model, and the prosody model also follows the exact same architecture. And yeah, the acoustic model predicts MFCC's F0 and periodicity features, which are fed into a vocoder. And the acoustic model itself is conditioned on speaker and language, and that's also the same for the prosody model. And then what we add in our paper are these yellow boxes. So we add a speaker predictor and a language predictor, and these both predict speaker and language. And then we add this GAN discriminator, and the GAN part and the multitask parts kind of work together in tandem. And I'll explain a little bit more about that later. So first, if we focus on the speaker and language predictors, you know, why have we added these? Well, our idea is that, you know, our motivation is that, you know, because for these monolingual data sets with only one speaker per language, speaker and language perfectly correlate in the data set. And so therefore the speaker and language conditioning information might be ignored. One of those vectors might be ignored by the acoustic model. Also, because the text encodings will look different between languages. I'll explain a bit more about those in detail later. But because they look different for each language, you could also infer the speaker and the language from the input features. And that also might additionally mean that these speaker and language vectors might be ignored. So to help the acoustic model to prevent it from ignoring it, these conditioning features, we try to predict from its vocoder features that it outputs speaker and language IDs. What is the architecture exactly for each of these predictors? So they're quite simple. It's just 5 1D convolutional layers. And the output layer is equal to, its dimensions are equal to the number of speakers or languages. And we just train that using a cost entropy loss with the ground truth labels. And yep, those, the losses from the speaker and language prediction are fed. They're used to train the predictors, but they're also used to update the acoustic model to try and encourage it to utilize the speaker and language input features. So why do we add this GAN discriminator then? Well, this is in tandem with the multitask learning. So the motivation is that there's a chance that the acoustic model may learn to hide the speaker and language input features somewhere in its output vocoder features in a imperceptible way. So in a way which doesn't sound like you're changing the speaker, or in a way where you're not changing the language identity in a perceptible way. So we're simply asking, the GAN discriminator is just trying to distinguish whether the features are real or fake. And hopefully we're hoping that kind of prevents the acoustic model from hiding, speaker and language somewhere in the bits of information that it outputs. And the GAN discriminator has I think a larger receptive field, so it's 10 convolutional layers, and it has a increasing dilation rate. similar to like WaveNet. And it outputs just a single value, predicting a number from 0 to 1. And that can be kind of interpreted as the probability that the input acoustic features are real. And we use the adversarial loss from this GAN to also update the acoustic model to prevent it from cheating. And so here's like the overall loss function. More details of each component can be found in the paper. But it's basically a reconstruction loss to help, and then the multitask losses to help the acoustic model utilize speaker and language information. And then we also have the adversarial loss, which tries to prevent the acoustic model from cheating at this multitask loss, task, or speaker and language prediction task. And so onto our experiments. The main question here is that we're trying to answer is, can the proposed model outperform a baseline in terms of naturalness? So we don't really focus on code switching or speaker similarity in our experiments because I think we were most focused on trying to provide new voice identities for low resource languages. And so we had two main types of baselines. One type of baseline are the mono-speaker acoustic models. So they train using only data from one speaker and one language. And then at test time, they receive input features from another language. And it can do this because they use phonological features. And then another baseline is basically the core multilingual model with multiple speakers, but just without the multitask or the adversarial augmentations. And then the vocoder which is shared across all models, is a multi-speaker wave RNN. So what kind of training data did we use? We used voice talents sampled at 24 kilohertz. And we have 5 speakers, and each speaker speaks a different language. And in total, we have 80 hours. And what input features are produced by front end? Well, they use phonological features as motivated previously by Dan Wells and by Marley Stab. And these are encoded as multi-hot vectors. And as Dan said, this avoids the need for phone set mappings between languages. So for evaluation, we asked 900 raters. So they're not balanced between the different languages, but we just try to recruit as many as possible. And yeah, we used 50 stimuli per language. And so here are the results of the listening test. So the best improvement is here. So here in this column, SFR just means that we have a French voice and speaking from the German test set. So we're transferring the French voice to the German input features. And that's the best improvement. You'll hear some samples in a second. The worst model is here. So it's the English voice speaking Italian. I don't really have any strong explanation for why it performs poorly or slightly more poorly. But what I guess this does suggest is that at least the model isn't scoring better just because it's generally, clearer or louder or something like that, perhaps. And the proposed system, on average does slightly better. And I will go through some samples. So this is the French voice speaking German. So we have 5 samples here, and they will go they'll go from left to right. So this is the baseline singles. Actually, I'll exit the presentation for 1 second and just play here. Okay, so here's the baseline single speaker.
Welchen von 8 Cousins meinst du?
And here's the baseline multi-speaker.
Welchen von 8 Cousins meinst du? Welchen von 8 Cousins meinst du? Das liegt bei der Zuwandtambelzukunft. Das liegt aber zu weit in der Zukunft. Das liegt aber zu weit in der Zukunft. Wie ist der Nachname von Teradna, Costa, Schindler Fontana? Wie ist der Nachname von Alaina, Costa, Schädlein oder Fontana? Wie ist der Nachname von Alaina, Costa, Schädlein oder Fontana? Welches Lied meinst du genau? Welches Lied meinst du genau? Welches Lied meinst du genau? Hier sind ein paar Beispiele für mögliche Sprachbefehle. Hier sind ein paar Beispiele für mögliche Sprachbefehle. Hier sind ein paar Beispiele für mögliche Sprachbefehle.
And here are some samples of our Spanish voice speaking English.
To get YouTube, go to Portal Apps and download it from there. To get YouTube, go to Portal Apps and download it from there. To get YouTube, go to Portal Apps and download it from there. Sorry, I can't do that yet. Sorry, I can't do that yet. Sorry, I can't do that yet. Okay, alarm set for tomorrow at 7 a.m. Okay, alarm set for tomorrow at 7 a.m. Okay, alarm set for tomorrow at 7 a.m. Device locked. Enter the passcode. Device locked. Enter the passcode. Device locked. Enter the passcode. Calling Mimi Diamond. Calling Nina Diamond. Calling Nina Diamond.
Unfortunately, I don't have any kind of ground truth samples from the English voice here to compare to, but they kind of sound like kind of closer to the Spanish voice than the English voice, but it's kind of a slight hybrid.
To get YouTube, go to Portal Apps.
Slide. Okay. So conclusions. So I think these monolingual speaker corpora are very difficult to model in general, and I think there's still much work to be done, especially in terms of like speaker similarity and that kind of thing. I think for further work, I think we should definitely demonstrate like using code switching and also some kind of speaker similarity test. I think that's probably number one to do. Another thing we wanted to do but couldn't due to lack of time was extend these other tasks to the prosody model and see if that was like, if that would change the prosody significantly. And then the other thing is, another idea is to use data augmentation methods to further improve disentanglement so that we go from this kind of monolingual single speaker data set to a multi-speaker data set for each language where some of those speakers are synthetic. And that is my presentation. Thanks for listening. Are there any questions?
Good, thank you very much. So Jason, you have already have a couple questions in the chat window. Also provide in the room as well.
Okay. It's the first question from...
Yeah, from Alexei. Speaker identity seems to slightly change in the third column. How to show without difference as a presenter set, but compared to column 1 and 2. No, sorry, I was looking at. Could you answer these questions? He was asking whether these are statistically significant or not.
So I think, we unfortunately didn't do any speaker similarity tests. And I think you're right, Alexis, that the speaker identity did change. I think part of the reason for this could be the fact that we've got this GAN real/fake task, which maybe is perhaps guiding the model to like kind of only synthesize from the seen speaker identities and the way that they pronounce their native language. I think some further investigation is needed here to really clarify that.
We also have questions from the room. Esther want to ask questions for you.
Hi, I was wondering, you were saying there were some issues with the English voice, and I was wondering if maybe it had to do with the imbalance in the amount of training data that you had for the different languages, because it said like there was 30 hours of speech for English, but then for some other languages there was only 5 or 7 hours or something.
Yeah, that's a really good point. I think we should have probably tried to balance the data sets to get fairer results. But I think we were kind of also aiming for like maximum voice quality. So that's one reason why we decided to include all the data. I think another reason was that in our data pipeline, there wasn't an easy way to kind of exclude data without excluding like entire domains. So we didn't want to train on like kind of a very neutral, unexpressive domain, which would have been the choice at that time. But yeah, that's a very good suggestion. Thank you.
Good. There's more questions in the chat window. Javier asking whether your speakers are all females.
Yes. Yep. All the speakers were female. Yep.
Yeah, and then Adrian asking, both Germans and English voices sound seems similar in your models. Maybe she meant sound similar. I don't know. Do you think the models learn sort of idem voice does not preserve the original speaker identity?
I'm not sure. That's a good question. I'm not sure if it's learning an eigen voice, but I think for sure it's not preserving the original speaker identity. I think, so the model would have to be changed if we were to focus on like the code switching application. But I think for their application, it's okay because they just focus on creating more voice identities. So actually, as long as it's different from the original native speaker, then that's okay. If it's like audibly different. Yeah.
I also have one question. So you have adversarial losses on the languages, but some of the English samples sounds accented. So probably your adversarial losses didn't perfectly remove those kind of informations, unfortunately. Can you guess how you can improve this point further?
So we had one idea which didn't yield any fruit, unfortunately. But the idea was to try during training, try to actually synthesize using speaker and language combinations not seen. And although we don't have any ground truth acoustics for those unseen combinations, we at least know that they are, you know, we know that they're fake, right? So maybe you could introduce either maybe a new GAN head, which is trying to recognize whether those unseen combinations are fake. And then, you know, we want the acoustic model to trick it. That's a potential way. But I think another question is, do we actually want them to sound fully unaccented? Maybe,
yeah,
maybe there are some applications. Yeah. I don't know. Good question though. Yeah.
So there's another question from Rob. Can you show the merge speaker tasks affects the primary output? Don't just cause the models to partitions the representation to run the tasks separately.
Yeah, I think we didn't have time for ablation studies, but I think that's quite a strong limitation of this work. I think that's a good question. That's a good point.
Yeah, probably it's useful to have some kind of like a studies of the embeddings to make sure that you have language independent representations. Yeah.
For Alexis, I think it's just phonological features. So there's no language specific phone sets used.
Are there any questions from the rooms? Okay, good.
In fact, I have a general question, which is in fact span the two papers. Just for me to understand, your phonological features are not phonetic features. It's some kind of ideal realization of the phones? Or is that actually the phonetic features that have been used by the speaker? Is that just some phonological score, which is just part of a lexicon? Or is that what the people have actually pronounced? Because the choice of, for example, the degree of openness of vowels, the degree of, how to say, voicing assimilations and so on is part of the identity of a speaker. So I was confused. I didn't ask a question in the previous paper, but so yeah. So what is the importance, because you train the system with this, of this phonological representation? Is that ground truth, or is that just coming out of a lexicon?
Good question. So I think short answer is it's kind of lexicon based, so it will be losing a lot of the nuance that you mentioned. Yeah, so I think maybe in the future, maybe there could be some work for like a way to transcribe a lexicon, maybe which just has more nuance and doesn't collapse down. Sorry, you're muted, sorry.
Sorry, yeah, we cannot hear you.
Yeah. You can't hear us, I guess.
Gerald, sorry.
Features. So yeah, okay. So
okay.
Sorry, Gerald, we cannot hear you about for 1 sec. So we saw that you were asking questions or comments, but we couldn't hear you about for about 1 second. If you don't mind, could you repeat the last questions?
I thought that you were not you were not how to say answering. So in fact, in the speech synthesis community, we seem to move from character input to phonetic input, and now to phonological features input. And by doing this, in fact, we specify more and more the way sounds are actually, or linguistic input is pronounced by the speakers. So I think it's dangerous, because if we, so either you stick to what has been pronounced, or yeah. So I just want to have your feeling about this. So there is a trend, in fact, of somehow before it was end-to-end, so everything was implicitly. So you give the system the opportunity to adjust and to learn how we implement, in fact, linguistic content. Nowadays, you specify more and more, and so the question is, who is responsible nowadays for style information, phonological choices made by the speaker, contextual information that gives, in fact, the proper variation of the articulation, in fact, given by the context. So I want to have the general feeling of your group, which are okay. So
good questions. Yeah.
Good question. I don't have a grand.
We have also durations and so on. So we are losing this idea of end-to-end synthesis. So did you discuss this in your group, or?
I think with my original collaborators, not really. I don't really have a grand philosophical answer for you, unfortunately. But yeah, I do think that a lot of the nuance is lost in this kind of like transcription process, whether that's to phones or to phonological features. So maybe, I don't know if there's a data-centric approach or some of a linguist approach to kind of creating more nuanced things. I don't know.
So it's a matter of discussion for this for the late afternoon.
Oh,
okay,
thank you.
Thank you.
Good. So Jason, could you also quickly answer the 2 questions in the chat window before we close this session, please? Javier
is that about these?
And Chan ask questions. Could you also quickly answer them, please?
So Javier, so for the speaker and language embeddings, I think it's the inputs to the prosody model and the acoustic model. It's kind of conditioned everywhere, if I remember correctly. I haven't looked at that code in a while, but I think it's also on the basically on every single thing. The vocoder, the acoustic model, all that, everything pretty much. I'm not exactly too sure about the details of where it is in the attention mechanism. For Tien, yeah, I'm sorry, but yes.
Last question is, do you have a sense of the relative importance of the multitask learning versus adversarial training?
Unfortunately, no. I think, again, we should do some stronger ablation tests there. Thank you.
Okay, so I understand we already ran out of time, but if you want to ask very last minute questions, it's a good time to do so. If not, we may close the sessions, but okay. Then thanks to sessions. Thank you very much for your presentations.
Thank you.
Thank you for the presentations, and also thanks to Junichi, who is like after midnight at home. So I know that in Japan you work long time, but I think it's more than average. So thank you very much.
You're welcome. Yeah.